Welcome to the UEA London Lecture. My name is Mark Searcy. I'm Professor of Medicinal Chemistry, and from Monday I'm the new Pro Vice Chancellor for Science at UEA. But today I'm here in my capacity as head of the School of Pharmacy and the School of Chemistry. And as head of the School of Chemistry, it's been my pleasure to play a role in the establishment of physics as a subject at UEA. And our lecturer this evening was the first appointment in the new physics area. And he was a great catch, as I'm sure you'll see. So I'm delighted to see so many alumni, friends, supporters and prospective students here this evening. And also a very warm welcome to those joining us by the live stream. Before I introduce our speaker, I'd like to make a small request of you. We'll be sending a brief survey via email to canvass your views on tonight's event. It would help us very much in planning future lectures if you could take time to tell us what you think. And if any of you are social media gurus and are on Twitter, we'd also encourage you to tweet your views. You can use a hashtag of UEA Live Lecture. I never thought I'd ever be standing here talking about hashtags. For the benefit of those of you who are new to these lectures, the format will be roughly as follows. Rob will speak for about 45 minutes. Then there will be time for questions. And finally, we hope you'll join us for a drink in the foyer. Now to introduce our lecturer. Rob is a lecturer in physics based within the School of Chemistry at UEA. He obtained his doctorate from the University of British Columbia in his native Canada. He then took up a postdoctoral position within the Observatoire de Paris as part of the radio astronomy group in Orléans. Here he performed high precision timing analysis of pulsar data obtained from the Nancy radio telescope and led pulsar data analysis software development. Following his time in France, Rob held research associate positions in the UK at the University of Manchester and at McGill University in Montreal, Canada, where he was involved in global efforts to directly detect gravitational waves. He returned to the UK in 2016 to take up his lectureship at UEA. Rob's principal area of research is in the observation-based studies of pulsars, the neutron star remnants left behind after massive stellar collapse. We detect their radio emission beams every time the beam sweeps past our planet like a cosmic lighthouse. They often display outstanding rotational stability, approaching that of atomic clocks over timescales of several years. Precision timing of these radio pulses enables Rob and his colleagues to address many questions in fundamental physics and astrophysics. And I think that's part of what he's going to tell us about this evening. So please join me in welcoming Dr. Robert Ferdman to give tonight's UEA London Lecture.
Hi, thanks, Mark, and thank you to the Alumni Association for hosting me here. I'm really, really jazzed to be here. It's going to be really fun. So today I'm going to talk about, I got to stand here. Today I'm going to talk about the most awesome objects in the universe, and those are pulsars, and I'll explain what they are and how they were discovered, what they are, and what we can use them for in addressing several, as Mark mentioned, problems and outstanding questions in fundamental physics and astrophysics. But our story begins way back in the 1930s when this wonderful gentleman, his name is Fritz Zwicky. I don't know if anybody has heard of him, but he was a very, shall we say, flamboyant physicist at Caltech. He's a Swiss astronomer, theoretical physicist, and he made a number of really forward-thinking advancements to our understanding of the universe. For example, he was one of the first people to posit the existence of cosmic rays, galaxy clusters. This is around the time that we actually just figured out that galaxies are outside our own Milky Way. Gravitational lenses, dark matter. This is really, 40 years ahead of his time. But what we'll be talking today is the subject of neutron stars and supernovae. And he was one of the central figures in the 30s to predict that these would exist, even though they were not discovered for some time after that. So we'll start with supernovae. Most of you have an idea, I hope, of what a supernova is, but I'll go over what causes it. In a star, the pressures at the core of the star are so high that what happens is we're fusing hydrogen at a high rate, and it turns the hydrogen into helium. And what that allows the star to do is to balance against balance an outward force against the inward pull of gravity, because these stars are really enormous things. And that keeps the star from collapsing in on itself. So the radiation pressure due to the emission of energy thanks to this fusion process. Once all the hydrogen is used up, the star will then move on to higher mass elements, helium, which which fuses into carbon, and then we just move up the chain of elements in the periodic table, as Mark would appreciate as a chemist. And we get all the way up to iron. Now, iron's special because unlike elements before it, when you fuse iron, you don't gain energy. It actually takes energy to fuse iron. You have to input energy. And that's a problem because the whole idea of this star keeping from collapsing is that we want to output energy to resist the gravitational collapse. So what happens is now there's nothing stopping the star from collapsing. And what happens as a result is you get this wonderful event, which we call a supernova. And what happens is the dense material that's collapsed in on itself is so dense that the infalling matter from the outer reaches of the star bounces off that inner really dense layer at shocking speed. Literally shocking, because what we have are these shock waves propagating outwards. So a supernova is how massive stars end their lives. Stars like our sun will not go supernova. They'll just quietly turn into white dwarfs eventually. But there are two types of results from a supernova. So you have stars which are between 8 and about 20 times the mass of our sun. Those will turn into what we call neutron stars, which is what Fritz Zwicky and his friends predicted. And anything greater than 20 solar masses, the probability is that will go directly into a black hole. So this is the Cassiopeia-A supernova remnant. Right at the center here, we see that there's a neutron star. You can actually see that in X-rays. And this is what we call the Crab Nebula, or M1, for those amateur astronomers in the audience. And at the center here, we also have a neutron star, and there's generating these powerful winds which energize and illuminate the nebula. So what we'll focus on in this talk is the neutron stars, because that's what this talk is about. So Fritz Zwicky has a really nice quote, which basically says that until we see things, we can do all the theorizing we want, but until we see things, we actually don't know how things work, and then what we're theorizing is actually valid. So as a theorist, he decided to take up some observational astronomy and went to the telescope and found images like this. So this little dot here wasn't here not too long before this image was taken. And the reason for that is that this is the result of a star that went supernova. And a supernova actually will outshine, in most cases, its host galaxy. So you can actually see them quite clearly. He actually found hundreds of these, over 100 of them, and up until not too long ago, he was actually the record holder for the most observed supernovae. So we fast forward 30 years later. So up until 30 years after Zwicky's time, these theories of neutron stars and black holes as well, and dark matter, they were all just sort of interesting theoretical curiosities. And the idea is that neutron stars were so small that we probably wouldn't be able to observe them anyways. They wouldn't be able to shine enough with enough intensity for us to detect them on Earth. However, 30 years later, along came a postgraduate student named Jocelyn Bell-Burnell. And by the way, if you ever get a chance to see Jocelyn Bell-Burnell give a lecture, please go. She's fantastic. But at the time, she was a postgraduate student at Cambridge, and she helped build a big radio telescope to try and detect quasars and scintillation of quasars, which was also a hot topic at the time. But what she ended up finding out is that she looked at some of her chart recordings. So it's basically, at the time, the radio telescopes, basically the output data were these chart recordings, which was basically a needle on a chart, sort of like a lie detector. And it just showed what the signal was at any point in the sky. So she found this and had no idea what it was. And the interesting thing about this, this signal is that these blips here came precisely once every 1.337 seconds without fail. And not only that, so this is why we end up calling them pulsars, because these are like little pulses. Not only that, but the width of these pulses was also really small, about 16 milliseconds. So what this tells us is that the thing that's producing them has to be a really small thing, coming from a really limited space. Probably something that's no larger than a planet. And so when people hear that there's this new thing that's emitting something with like this astonishing regularity that's no bigger than a planet, what do they immediately think? But this theory of aliens was it wasn't a total joke. I mean, it could have been, but it was put to rest pretty quickly because Jocelyn found a similar source in a completely different part of the sky not too long after that. And then she found another, and another, and then another. So the thinking was, it was highly unlikely, as she put it, that several lots of little green men would all be signaling to us, all at this exact same radio frequency, and all at exactly the same time. That would be the most extreme of coincidences. But still, people didn't really understand what these signals were. But it didn't take too long for people to figure it out. They were neutron stars. And these pulsars are neutron stars that we can actually see. And the way we can see them is they emit radiation from their magnetic poles, as you can see in this diagram. And they rotate on an axis. And the axis of rotation is, in general, not exactly aligned with the magnetic axis. So every time this pulsar rotates, if we're lucky enough to be in that line of sight, if it cuts through our line of sight, we see a pulse. Now the audio is there for effect, but basically this pulse happens extremely regularly. So some fun facts about pulsars and neutron stars in general. They weigh, in general, on average, about 1.5 times the mass of our sun, except that they're 1.5 times the mass of our sun, but they're in a region the size of London. We wouldn't want this to happen, by the way. Although it would be cool, but just for a second, and then it wouldn't be cool. So this thing that weighs 1.5 times the mass of our sun, but compactified into the size of a city, must be really dense, and it is. A teaspoon of neutron star material would weigh about as much as all of humanity, or Mount Everest or something big like that. So these are really, really exotic, extreme objects. There's more extremeness to them. The magnetic fields are over 1 million times stronger than anything we could ever hope to produce on Earth, or anything we currently can produce on Earth. If we were to put a neutron star at the distance of the moon, it would probably wipe out all the credit cards on Earth. So that's actually not so bad. And also, they spin really fast. Once per second is really fast, actually, but actually they spin a lot faster in some cases. Some cases they spin up to almost 700 times per second. So this is as fast as your kitchen blender. So you have something that's the size, 1.5 times the mass of our sun, size of a small city, can wipe out all the credit cards on Earth, and spins as fast as your kitchen blender. So these are truly extreme objects. And the fact that we see them once per rotation really does make them sort of like a cosmic lighthouse. And these are special cosmic lighthouses as well, because as I keep mentioning, the pulsars are very regular. And as Mark mentioned in his introduction, some pulsars rival the stability of atomic clocks over several year timescales. So, so these are truly useful objects as well. These are these really precise clocks in space. Now the key is we have to measure these pulsars. So how do we do that? We use instruments like this primarily, although we can measure them in other wavelengths besides radio, like X-ray, in some cases optical, but mainly pulsars are seen in the radio. This is the Arecibo radio telescope in Puerto Rico. It's a dish 300 meters across, so it's about 1 kilometer all the way around. So people actually, when I visited there, people actually like to go jogging around there. It's a good workout. We need dishes this big because the bigger your dish is, the more sensitive your telescope is, and that's because you can collect more light. The more light you collect, the more information you get, and the more sensitive your telescope is. So this is, until recently, the largest single dish telescope on Earth. Now there's one in China that's much bigger, 500 meters across, fast telescope. I've also used the Green Bank telescope. This is in West Virginia. This is 100 meters across, but it's fully steerable, whereas the Arecibo telescope is stuck in the ground, and you move this back and forth to point into different directions in the sky, and it's limited in its directionality, but this is not nearly as limited. You can see 80% of the sky over the course of a year. This is much more closer to home. I use this telescope extensively as well, the Jodrell Bank Level Telescope. This is 76 meters across, so it's no slouch at all. It's a really nice telescope, and if you get a chance to go visit the Jodrell Bank site, I highly suggest you go. It's really nice, and they have a great visitor center. Okay, so we observe the signal from these pulsars with our radio telescopes, and these pulses come extremely regularly. This is an example of actual data, not live, of course, but this is sort of what it looks like. The cool thing about this is that we can precisely measure the arrival times of these pulses. And because they come so regularly, we can actually count each rotation. So we can enumerate the rotations of the pulsar. And this is a very powerful tool. And we can do this for pulsars like our friend 1919 plus 21, which was the first discovered pulsar, 1.3 second period. We can do it for much faster pulsars. This is the Crab. There's the pulsar in the center of the Crab Nebula, rotates once every 33 milliseconds. I'll stop. But the point is that they're really precise clocks because we can do this. We can count each rotation of the neutron star. We know how many rotations. So here's another example, a more extreme example. PSR, the wonderful name, PSRJ 1713 plus 0747, which means nothing to most people, means a lot to us, rotates on its axis once every 4.6 milliseconds, which means we get a lot of pulses from it. So for example, between the dates 15th of August 1992 at this time and 23rd of November 2013 at this time, the pulsar has undergone exactly 457,495,457,989 rotations within this time. And that's without ambiguity. We know that without ambiguity. And this allows us to determine the rotation frequency or the rotation period of the pulsar to astonishing accuracy. So for this, we know that it rotates on its axis once every 218.811.843.85.472.54 hertz. And this is the uncertainty in that number. So these are really astonishingly accurate timekeepers in space, and we can use that to do really astonishingly high precision astrophysics. So we just count pulses and we do that, although the problem is it's not that simple. because the pulses on their way to Earth, there's a number of delays that they can undergo that we have to take account of. But it turns out that these delays that we have to take account of are really important, and these are the things that allow us to, in a sense, do the precision astrophysics that these pulsars promise to us. So, for example, one thing that causes delays is that Earth's orbit. So, at different points in Earth's orbit, it's at different distances from the pulsar. So, let's say at this point in its orbit, it's at some distance, and we get the pulses, at some time that we predict. At another point in its orbit, we get the pulses from the pulsar, which is, relatively speaking, more or less in the same spot between here and here. And as this diagram shows, the distance between the pulsar and Earth is quite different. And as such, we have to take that into account because the pulses will arrive later at different points in Earth's orbit. And in order to get that information and to model that, we have to know the pulsar's position quite accurately. And we do know the pulsar's position quite accurately. So here's an example. Before I moved back to the UK, I was living in Montreal. So I traveled all the way to the UK. It's about 5,000 kilometers away. I accidentally left my football, not soccer ball, football, in Montreal. Now, the angle that soccer ball subtends from London, so the angle it makes and the angle that it makes, if I were able to see it, is about the precision to which we can measure the positions of pulsars on the sky. And this is really handy because there's a lot of things that come in the future and currently come in handy by knowing the position to this accuracy and to this precision. For example, one active area of research is pulsar navigation, pulsar-based navigation. So knowing the positions of these pulsars in space to extremely high precision is really useful for perhaps setting up a sort of a galactic GPS system for monitoring the positions of satellites, for example, or spacecraft going elsewhere in our solar system. Some of you may know about the golden disk that was on board the Voyager spacecraft in the 70s. They put a golden disk here in case some other civilization picked it up that was able to, that was an intelligent civilization. And one of the things they used was pulsars in this part of the disk here. This is an image of showing, it's more of a diagram than an image, the position of Earth relative to some of the brightest pulsars in the sky. And you can't really see them, but there's ticks along here, and that sort of tells the aliens what the rotation period of the pulsars are, which is good information because we know that really precisely, so they can sort of triangulate and figure out where Earth is located. Another example of these delays, I won't go through all of them because there's many, but another example, a classic example, is that if the pulsar is moving, which it is in all cases, but some move faster than others for reasons I'll explain. So if the pulsar is moving, the pulses that, if let's say you're behind the pulsar in its trajectory, the pulses will sort of start to arrive later, or more spaced out rather. Whereas if you are in the direction such that if you're facing the pulsar and it's coming towards you, the pulses sort of will pile up and come more frequently. And this is due to something called the Doppler effect. Now, some of you may know what the Doppler effect is by standing on train stations. Oops. As the train passes by you, the pitch of the horn or the siren or whatever it is, in case of an ambulance, for example, will dip, so that if something's traveling towards you at some speed, the pitch will be higher than if it's traveling away from you. That's because of the Doppler effect, and it's the same effect, except in the case of pulsars, it's just that the ticks come more frequently rather than the pitch going up. And so one case where this happens quite frequently is that when the pulsar is in a binary system with another star. So if it's in orbit with another star, if the pulsar is moving away from you, the pulses will come at some interval. And then once the pulsar is moving towards you, they'll be coming more frequently. And then it just keeps doing this. And we can actually use this information to determine the properties of the binary system. For example, like its orbital period of the orbital period of the pulsar, the orbital eccentricity, so how elongated the orbit is, the size of the orbit, or the semi-major axis as we call it, the longitude of periastron, which means where is it and at its closest point to its companion. And we can learn a lot about the binary and this is important because about half the stars in our galaxy are locked in binary systems. So it's quite an important thing to know. Another cool thing about binaries, actually, sort of as an aside, is that if the pulsar is in a binary with a star like our sun, for example, that's not evolved into a neutron star or a white dwarf yet, what will happen if it's close enough to the companion star, it will start to actually suck matter from the companion star. It'll start to accrete matter that's donated by the companion star. And what this has the effect of doing is it'll spin up the star. So you can think of, let's say, a figure skater spinning. If you start tapping the figure skater and giving it energy by tapping the figure skater on his shoulder, you're actually spinning the figure skater up even more than it would, or he or she would. So this is actually how we get those pulsars which have 1 to 10 millisecond rotations. And so this was discovered, the first millisecond pulsar was discovered in 1981, and it has a nice name again, PSRB 1937 plus 21, and it has one turn every 1.557, okay, I'll stop. But it has a really short period, and it was the record holder actually until not too long ago. As of 2004, the new record holder is one called Terzan 580. Anyways, it has a rotation period of about 1.4 milliseconds. So these are really fast spinning things. One of the things, there are many things you could use pulsars for to study, and this extremely high precision. But one of the things that I like to study a lot, and a lot of my colleagues like to study, is to use them as probes of Einstein's theory to test general relativity, for example. And this happens in particular when pulsars are in orbit around other stars, especially if those other stars are white dwarfs or other compact objects like another neutron star, for example. Because the space-time of these objects is really much more affected and much more warped than in the case of, let's say, a sun-type star. And so you can test for effects that are predicted by general relativity and see if they pass the test. So if you have one of these relativistic binaries, the properties of the binary depend on the orbital characteristics and the masses of the stars. So some of the effects that we can measure actually are, for example, orbital precession. This is when the actual orbit changes orientation over time. And we know this happens. We knew this happened quite a while ago with Mercury, actually. We know that Mercury's orbit precesses as it goes around the sun. So as you can see, every time it orbits, it changes its orientation a little bit. And this is predicted by relativity, and it was predicted extremely precisely and accurately by relativity. Time dilation and gravitational redshift. So in a gravitational field, time will move faster than if it's in a weak gravitational field, weaker gravitational field. Orbital decay, so the orbit of the binary will shrink over time due to the emission of gravitational waves, and I'll talk more about this in a moment. And then there's another cool effect called Shapiro delay. So if the pulsar is relative to our line of sight, looking at the pulsar, if it's in a binary and it's at inferior conjunction, which means that it's behind its companion on a more or less edge-on orbit, the amount of space that it has to travel through, the distance it has to travel through is increased by a little bit. So you'll see a delay in the pulse arrival times because of that effect. And by measuring 2 or 3 of these effects, we can actually determine the individual masses of the system. And by knowing the masses as well as the other orbital characteristics, we can actually study binary formation and evolution and test models of how these stars actually formed and evolved over time. And then we can also do tests of relativity just by seeing if these match up what Einstein's theory has predicted they would come out to be. So not just because of pulsars, but because of other tests as well, Einstein's theory, which is now over 100 years old, has been spectacularly successful, passing every test with flying colors that's been thrown at it. But we know it's not the final word. So general relativity as one of the fundamental forces is not compatible with, for example, quantum mechanics or the standard theory of particle physics. So we know that it's not the be-all and end-all description of gravity, although it's the best description we currently have. So because of this, we actually need a variety of tests to determine where this theory might break down, and that could give us a clue on how to perhaps unify theories of fundamental forces. In particular, strong field environments such as those around pulsars and other compact objects such as black holes experience very different predicted effects that are actually observable, especially in the case of pulsars. So that's why this is one of the main reasons that we study pulsars so adamantly. And one of these effects has been in the news for a while now is gravitational waves. So I talked about orbital decay not too long ago. So if you have two neutron stars, for example, in a binary system that's close enough to each other, where the neutron stars are close enough to each other, the system will actually give off gravitational waves. And that energy that's carried off by gravitational waves has to come at the expense of something, and that something is typically the loss of orbital energy, and that's why the orbit shrinks over time. And so what we need is to find a system or systems that are appropriate for doing these types of studies to really test the strong field regime of general relativity, of Einstein's theory. And so this happened in the mid-70s when Russell Hulse and Joe Taylor, working at the Arecibo Observatory that I described earlier, discovered a new pulsar. And this was not too long after the discovery of pulsars, which was 1967, so 7 years later. They found the first pulsar in a binary system. So this is really cool, but what's actually extra cool is that this pulsar was in a binary system with another neutron star. What was even cooler is that it spins 17 times per second, but its orbital period is 8 hours. So it goes around once in orbit every 8 hours. And they're about 1 solar radius apart from each other. So they're really close in together. So this radius of the sun, that's how far apart they are from each other. And that means that the orbital speeds are really high, about 300 kilometers per second. And that's about 1/1000th the speed of light. And that seems like not too high a fraction of the speed of light, but it's actually really in the regime where it becomes important. And they realize that it becomes important to actually take into account the effects of relativity. And they realized that right away in their discovery paper, where they predicted that this would actually help us to test general and special relativistic effects and test the predictions of relativity. So they observed this pulsar over time. You can see the axis here. This is the only real plot I'll show on this talk. Going from 1975 to about 2005, I have this, although they're still observing it. And this here shows us how the period, meaning one full orbit, the time it takes to do one full orbit, how that changes over time. And so if Einstein is wrong and it just stays the same, that's what this line represents. So 0 change, that's what this is. And if Einstein's right, or if Newton is wrong, for example, then we should see a change in the orbital period every time the pulsar makes an orbit, because if the orbit is shrinking, the time it takes to do one full orbit will also decrease. And so they took the data over time and they found that it deviates from this flat line. So that's really interesting. And what they did was they compared it to relativity predictions, and it was bang on. And this is not a fit to the data or whatever, this is just the theory. In fact, it was within about 0.2%, they found that it agreed with the predictions of general relativity. So this is one of the plots, actually. I show this because this is one of the plots that got me interested in this. So they seem pretty happy, not least of which because, well, this is really one of the most amazing results in physics, I would say, in the latter half of the last century. But they also won the Nobel Prize for this result. Okay, but that's what we call an indirect detection of gravitational waves. It's an indirect detection because it agreed with the predictions of relativity based on what the theory says the binary should do as a result of emitting gravitational waves. It didn't actually see the gravitational waves in action. So what does that mean? So if a gravitational wave is passing through this screen here, and you have a bunch of these test particles in a loop, for example, what you'll see is a stretching and squishing over time. And the rate at which it does this stretching and squishing depends on the frequency of that gravitational wave, so the wavelength or the period of that gravitational wave. Here's a 3D. It's kind of cool, kind of creepy. But you can see how it works. And so we actually want to see this we want to see this happening in action. In terms of binaries, what would happen is the binary would shrink. And the prediction is that the binary would shrink. And as the binary shrinks, whether it's neutron stars or black holes, the amplitude of this wave would increase, but also the frequency would increase, so that the period would decrease, so that the peaks would come sooner and sooner and sooner until two objects merge together. I'll show you the video again. And then the gravitational waves cease. Maybe I'll go faster. Boom. Okay, so if you want a sound analogy, what happens is the frequency is increasing, which means it's a higher pitch, and the amplitude is increasing, which is analogous in terms of sound, for example, to a louder signal. And so what you end up with is a signal that goes, which we call, appropriately enough, a chirp. It wasn't that long ago, as most of you know, would hopefully know, that this instrument here, which is called the Laser Interferometry Gravitational Wave Observatory, there's two of them in the United States. One is in Louisiana and one is in Washington State. They found this signal. If you listen, you can hear the whoop, the chirp. And that's what this signal is showing. The amplitude's increasing and the distance between the peaks is decreasing, so the frequency is increasing. And this is just a reminder of the video. So what this means is that you have these two high mass things orbiting each other, and the orbit is shrinking, and we're catching it right at the moment where it merges. What these ended up being were two really massive black holes that merge together. And that's a completely other topic, because right now we're talking about pulsars. So how does this relate to pulsars? Well, we want to actually be able to detect gravitational waves with pulsars, and how do we do that? Well, we can start in our own galaxy, in the Milky Way. This is an image of the center of the Milky Way in the infrared, and this is an X-ray. We see this really bright thing in the center of the Milky Way, and what that is what we call a supermassive black hole, and it's about 4 million times the mass of our sun. So it's a black hole, but it's not stellar mass, it's 4 million times the sun's mass. So that's why we call it supermassive. And it turns out that every galaxy that we know of, especially every massive galaxy, has a supermassive black hole at its heart. Okay, but what we have to do is we have to go back in time. Excuse me. Back in time, in the distant universe, galaxies would merge more often. Galaxies would actually merge, and when they merge, the black holes at their center would interact, and when black holes interact, they give off these gravitational waves, just like neutron stars do. The further back you go, the more galaxies there are that merge. So you get more of these gravitational waves. And if you go back far enough, you guessed it, there's lots of galaxies that merge. And we get lots of these gravitational waves being emitted by interacting black hole binaries, supermassive black hole binaries. And there's so many of them, we can't actually, and these are distant enough that we, in general, can't hope to detect individual ones. But what we get is what we call a gravitational wave background. So it's like, you can think of it as like a bath of gravitational waves flooding the Earth. The frequency of these gravitational waves is in the nanohertz regime. So that corresponds to a wavelength, so peak to peak, trough to trough of the waves of light years. So these are really long waves. And light years means that we need something that we can use over many years time scale to observe these gravitational waves. If only we had really accurate clocks in space. So pulsars are, you get, spoiler alert, they're pulsars. So what happens is we get these pulses at Earth, and they're really evenly spaced, really regular. As a gravitational wave passes by Earth, what happens to these pulses is that they're affected by the gravitational wave such that they arrive sooner and later at a rate that depends on the wavelength of the gravitational wave. And so what we do, and this is just a reminder of the stretching and squishing, this is just a direct result of that. So I'll put this up again. As the gravitational wave passes by Earth, we get this stretching, and we detect this stretching and squishing of the times of arrival of these pulses. And so our aim, one of the major collaborations I'm involved in, observes many pulsars distributed all over the sky in what we call a pulsar timing array. And what we aim to do is determine, because we're talking about a gravitational wave passing by Earth, by observing different pulsars all over the sky, we should observe a common effect in the timing for all the pulsars that we observe. So again, there would be a correlated effect on the effect of the gravitational waves on the arrival times of the pulses. And that's what we aim to detect. And so by detecting the gravitational wave background, we can actually do a lot of really interesting astrophysics. We can study galaxy formation history, because this is as a result, these gravitational waves are a result of the mergers of distant galaxies in our early universe. So we can actually study how these galaxies formed and evolved over time. And that includes how they formed stars. It includes studies of dark matter, how that plays into it. We can study the supermassive black holes themselves, because as you can imagine, these black holes that are so massive, it's a mystery how they got that massive. It's not just like a bunch of stellar mass black holes got together and made a 4 million solar mass black hole. And because we're studying things in the early universe, this directly has an effect on our understanding of cosmology and the evolution of the universe. Okay, so I'll talk a little bit, in the time we have left, I'll talk a little bit about the future of pulsar observations and gravitational wave observations using pulsars is what we call the square kilometer array. So the square kilometer array is, as the name suggests, an array of radio dishes in South Africa and in Western Australia. It's going to be the world's largest radio telescope. In fact, I think it will be the world's largest scientific instrument when it's completed. It's going to be about 10 to 100 times more collecting area, and thus 10 to 100 times more sensitive than the current state of the art. And the enormous data rates that are involved here require some forward thinking in terms of computing power and computing techniques. So for example, this telescope will be so sensitive that we'll be able to detect an airport radar on a planet tens of light years away. The data rates are comparable to the internet traffic on Earth. And we're going to require a supercomputer that's equivalent to over 100 million personal computers. So this is really like state of the art. So this is a good answer to the question: is what good is astronomy? Well, apart from the fact that it's super interesting, it actually drives a lot of this technology as well. Currently in the SKA, there's 11 full member countries, although I think that number's increased now. As I mentioned, it's going to be located in South Africa and the Western Australian desert. We're going to be studying different wavelengths of radio waves at these two different locations. The world headquarters is located here in the UK at the Jodrell Bank Telescope site, which is near Manchester. And all the major universities in the UK that are doing radio astronomy are contributing to the SKA in one way or another. Okay, so that brings me to the end of my talk. That is just the tip of the iceberg of what we can study using pulsars. I haven't mentioned a lot of things. We have these collections of stars in our galaxy called globular clusters, which have 100,000 stars in them, and they're the oldest populations of stars in the galaxy. It turns out there's lots of pulsars in those objects, and so we can study the globular clusters and thus the formation of the galaxy even using pulsars. Pulsar glitches. So these are some pulsars are actually seen to spontaneously or instantaneously change the rotation rate to a much higher frequency. And that gives us clues about the interior, the exotic interior, because it's highly dense matter we're talking about in the interior of the neutron star. A lot of you may not know this, but the first planet that was discovered was actually in orbit around a pulsar. And we were able to determine that it was there because of the precision that pulsar timing affords us. Magnetars are a type of neutron star that, as the name suggests, are the most magnetic objects in the universe. They're about 1,000 times more stronger magnetic field than pulsars, than normal, so-called normal neutron stars. X-rays and gamma rays are another two wavelengths, or energies rather, that we can study pulsars at. And they've revealed a wealth of new pulsars that we didn't even know existed, because some are actually radio quiet, as we call it, but do shine in a gamma ray and X-ray. There's rotating radio transients, which are, we believe, are neutron stars or pulsars that only actually emit once every so often. And so these are peculiar objects. They're extremely interesting. And of course, fast radio bursts have been in the news lately. These are these one-time, or in general, one-time only bursts that we believe are occurring in galaxies very, very far away, and that bring with them extraordinary energies, and we still don't know exactly what they are or what's causing them. But that's a completely other talk. But for now, we talked about Einstein, and hopefully one day, using pulsars or some other methods, we'll be able to challenge his theories and find out where these theories break down. And I will leave it there. Thank you very much.
Rob, I'm sure Rob would be happy to answer any questions.
Hello. Hi. Thanks for a really interesting talk. You talk about long time scales. I'm just wondering how all this studying of these minute entities is affected by our ever-expanding universe. Things are getting further apart rather than closer together.
At the moment, not very, because with a few exceptions, all the pulsar signals are extremely weak. And that's why we need those really large radio telescopes to observe them. And that means that, with a few exceptions, all the pulsars that we know about are in our own galaxy. And so the expansion of the universe doesn't really play into their behavior as such. But one day, we'll be able to hopefully detect pulsars in galaxies beyond our local group of galaxies and use them as probes. But these fast radio bursts actually could be cosmological tools because they're actually at very, very vast distances. So that remains to be seen. So if you're interested in that, keep an eye on those.
Thank you. What is thought to be the ongoing energy source for the emissions?
It depends on what type of pulsar you're talking about. Most pulsars are due to the, so I said that the pulsars are rotating with remarkable regularity, but in fact they actually are slowing down extremely slowly. In fact, they slow down, the average, the number we throw around in these public talks is that pulsars generally slow down by about a second since the age of the dinosaurs. So they slow down really, really slowly. But the fact is we can measure that slowdown rate using pulsar timing. And the energy that's lost in the pulsar rotation comes out because of comes out in the emission. And that's what powers most pulsars, which we call rotation-powered pulsars. In the magnetars that I showed on the last slide that I didn't even talk about, the emission from those is due to decaying magnetic fields and that sort of thing, because the magnetic fields in there are crazy. But those are two of the main sources of energy that powers pulsar emission.
Has the death of a pulsar been observed?
The death of a pulsar. Pulsars are already dead stars. But I know what you mean. You're talking about turning off, pulsars turning off. No, because that hasn't been observed directly. It's been inferred, although those theories about when pulsars turn off is being thrown on their head right now, because it was thought that if pulsars rotate less than once every 8 seconds or 10 seconds or so, beyond that they won't really shine anymore because there's not enough energy to power the emission. But we found now pulsars with 20-something second rotations and even larger rotations now. So, and then we have these RRATs, these rotating radio transients, which only show one pulse sporadically. So the ideas behind when the pulsar dies is more complicated than we thought.
I'm interested in the binary pairs, and you mentioned frequencies and orbital rotations and speeds, etc. But if they're two dense objects with high gravitational fields, doesn't that speed up time? And how then do you measure speed and frequency with variable time?
Yeah, so that's part of when we're measuring the arrival times of those pulses. Those would be affected by those effects, absolutely. And so that's part of the model that we apply to the pulsars to determine the magnitude of those effects. And so those are taken into account when we time the pulsars. But definitely time dilation, gravitational redshift, those are all taken into account. They have to be.
Thank you. Rather an esoteric subject, and I'm glad I didn't study maths and physics at UEA, but very interesting nevertheless. I have a kind of unscientific question.
Okay. An unscientific answer.
It's as a child, or even now, when you turn a radio set on,
yeah,
there's what I assumed was static. But I suspect these were neutron kind of stars sending their signals and the radio receivers were picking up. So have our radios any use for us other than to just pick up static?
Yes, sort of. The sensitivity of radios is probably, like your home radio, is probably not high enough to detect pulsars, for example. But if you flip that on the other way, the transmission towers that provide radio signals from radio stations and TV stations, those are the bane of our existence, because our telescopes are so sensitive that they easily pick up those signals and they wash out other astrophysical signals which are incredibly weak. So we always have to put these radio telescopes in places that are extremely radio quiet. Otherwise, we're going to miss a lot of those signals. But your home radios, definitely probably not sensitive enough to pick up most astrophysical signals. But it has been known to happen. What's a good example? So these magnetars, again, this talk is not about magnetars, but it keeps coming up now. These magnetars, every so often, they emit what are called giant flares. And these are so energetic that there was a case or two in which those giant flares affected the ionosphere of Earth, and that affected actually shortwave radio signals on Earth.
Thanks. Apologies for mentioning Brexit, but let us suppose I
was keeping away from that.
In a year or two's time, the government does actually realise that it needs to do rather more to encourage international scientific collaboration, including the UK. Yeah. Your area is one which clearly includes a lot of international collaboration and a lot of really big kit. Yes. You've mentioned Jodrell Bank and the SKA headquarters. Yeah. If the government were to put out a request in a year or two to say, actually, we're going to invest a large amount of money in a big bit of globally important physics kit, what would you be bidding for UEA and why?
For UEA, mark over your ears. Well, like you said, these are really international collaborations, and so a single university probably is as you mentioned, is not quite large enough to fund a telescope like the SKA or even like an Arecibo, for example. It needs a collaboration. So I would definitely would not just be talking about UEA, although I would want UEA to play a big part, but I would probably want to put in proposals and grant and so on with other UK universities and other international collaborators. But yeah, Brexit is a hot issue with everybody, but it is also a hot issue among scientists, and we are worried about what funding is what's gonna happen with funding once Brexit happens, because as you all know, it's all up in the air at the moment.
Thank you for your lecture. This is another totally unscientific question. Okay. Pulsars are the total end point of a dead star. Do they have the power to regenerate? You said, I think, at some point, some of them spin so fast they can attract matter. Do they regenerate? And then a second part to that question, you said our sun will not become a pulsar. Why?
Okay, so the first part of your question, absolutely they do. They regenerate in the sense that even once a pulsar dies, and if it rotates too slowly to produce emission, if it's in a binary, a close enough binary with another star, and it accretes that matter, it'll spin up again, and that's what we call recycled pulsars. That's why we call them recycled pulsars. And when it spins up enough, we believe that that's what's causing these pulsars that we see that are millisecond periods. And so in that sense, they could regenerate and shine once again. In terms of the sun is not massive enough to turn into a neutron star. So the gravity, when gravitational collapse happens, the mass is not high enough for the collapse to continue through to getting the highly dense neutron stars. You still get a highly dense object called a white dwarf, but those are Earth-size objects, which are still quite compact, but not as compact as a neutron star. And that's because the physics behind what stops it at that Earth size is different because of the mass of the star before it collapses. So a star's life is basically determined by its initial mass.
If the signals from the pulsars are directional, do we only see them when they come our way?
Yes.
And if they're not spinning, if they're progressing as they're spinning, would it move away from us and then maybe sometime later come back?
Yeah. So depending on how wide the beam is, We would only see it if it cuts through our line of sight. And yes, pulsars move, but they don't move enough to really substantially affect our view through that beam. However, if a pulsar, again, is in a relativistic binary, there's an effect that I didn't mention called geodetic precession, which causes the pulsar spin axis to actually spin like a top on a table. Like when you spin a top on the table, the spin axis actually rotates itself. And that could actually cause the beam to move out of our line of sight and then eventually back into our line of sight again. But that happens over decades or hundreds of years. But it's something that we can actually measure happening, even though it might. There are pulsars which we have observed to move out of our line of sight, but we can also measure how the emission changes because that's happening. So we know that that does happen. And that's also a relativistic effect that's been verified using pulsars.
Hey, you mentioned that the first pulsars were discovered effectively by hand or by reading the results of these telescopes. I was wondering to what extent machine learning or any kind of AI was being employed to detect new pulsars, especially with the effects you said of other radio interference and stuff like that.
That's a really good question. And in fact, that's a really active area of research at the moment, is using machine learning to discover pulsar signals. And also another active area, and something that I'm interested in as well, actually, and embarking on in conjunction with people at UEA who are in computer science, is to use machine learning to differentiate maybe pulsar signals from radio frequency interference, so we can actually more easily get at the real pulsar signals and other transients like fast radio bursts, for example. But yeah, that's a very hot area right now, and highlights the fact again of the innovation that goes on in astronomy beyond just understanding our universe, which is why we all study it, but also it contributes to innovation. That's why we recruit people like from computer science more and more often. One more.
Good evening, Dr. Ferdman. Thank you for the insightful talk. This might perhaps be another unscientific question, but this relates a bit to the understanding of the cosmos part. So what I understand is that all this talk about, like we've been talking about pulsars and radio blips and binary systems and so on. I think in the common parlance, it's a bit of a niche area. Like there are people, like it's more mostly the academia is concerned with dealing with these problems. So if I'm not digressing, could I ask you your views on how one could make the interest of people more widespread in this area?
So if I understand, you're asking how can we bring it out of just academia and make people more interested in it. Well, that's what we try to do with talks like this. At UEA and in Norwich, we have, for example, science weeks, where we have people giving talks and demonstrations, and we're always quite open to getting interest from the public and soliciting interest from the public. We also, for example, high schools, we have work experiences over the summer with high school students to get them interested, and in particular underrepresented groups in sciences as well. So that's something we actively do as part of our job, and it's something that we actually are very interested in doing, is to bring it to the public, such as yourselves. And why wouldn't we? I mean, we really enjoy this topic. Why wouldn't we want to share it and tell everybody what we're doing?
Okay, everybody. I think you'll agree that it's really good to know from Rob's talk that that we'll still be able to use Google Maps in our spaceships because we'll be able to use the pulsars. And I don't know whether you know, for a Star Wars geek like me, the comment at the end about I think it was the bursts that are far away. Rob did actually use the expression "galaxy far, far away," and clearly those bursts are the Death Star blowing up again and again and again in all the sequels. Please join me in thanking Rob again for the talk, and also please join us in the foyer for drinks afterwards. Thank you.